Please subscribe to support the channel. The question of how long it takes to leave our solar system stands as one of the most profound inquiries humanity can pose about our place in the cosmos. It's a question that simultaneously humbles us with the vast scale of space while inspiring us with the audacity of our exploratory spirit. When we look up at the night sky, we see stars that seem tantalizingly close, scattered across the darkness like nearby islands in a cosmic ocean. Yet the reality of the distances involved challenges every intuition we possess about travel and time. This question captivates us because it represents more than just a technical calculation of velocity and distance. It symbolizes humanity's first genuine steps beyond the cradle of our birth, our initial venture into the true wilderness of interstellar space. For all of recorded history, humans have lived within the gravitational and radiative embrace of our sun, never venturing beyond the protective bubble it creates around our planetary neighborhood. To leave the solar system means to cross a threshold that separates us from everything our species has ever known, entering a realm where the sun becomes just another star among countless others, where its warmth and light no longer dominate the environment, and where we truly become travelers in the galaxy rather than simply inhabitants of a single star system. Understanding how long this journey takes requires us first to grapple with a surprisingly complex question that lies at the heart of the matter. What exactly do we mean when we talk about the solar system's edge? This might seem like it should have a simple answer, but astronomers and planetary scientists have debated various definitions, each with merit, and each yielding dramatically different answers to our central question. The solar system isn't like a country with clearly marked borders or a city with defined limits. Instead, it's more like a sphere of influence that gradually fades as you move away from the sun, with multiple transitional zones marking different aspects of where that influence diminishes. These boundaries aren't physical walls you could touch or see, but rather invisible thresholds where different forces and phenomena dominate the environment. The challenge in answering our question stems directly from which boundary we choose to recognize as the true edge of the sun's domain. The first and perhaps most intuitive boundary many people think of is the orbit of the outermost planet. For most of the 20th century, that would have been Pluto, sitting approximately 3.7 billion miles from the sun at the farthest point of its elliptical orbit. However, since Pluto's reclassification as a dwarf planet in 2006, Neptune now holds the title of outermost planet at about 2.8 billion miles from the sun. Yet using planetary orbits as our boundary feels somewhat arbitrary and unsatisfying. The solar system clearly doesn't just end where the last planet orbits. The sun's influence extends far beyond Neptune in multiple ways, creating a much larger sphere of dominion than the planetary orbits alone would suggest. This realization leads us to consider other, more scientifically meaningful boundaries that better capture where the solar system truly transitions into interstellar space. The heliopause represents what most scientists consider the primary, functional boundary of the solar system for practical purposes. This invisible boundary marks the point where the solar wind, that constant stream of charged particles flowing outward from the sun at speeds of roughly 1 million miles per hour, finally meets and is stopped by the interstellar medium, the thin soup of gas and dust that fills the space between stars. To understand the heliopause, we need to appreciate that the sun isn't a passive ball of light sitting quietly in space. It's an active, dynamic star that constantly ejects material into its surroundings. This solar wind consists primarily of electrons and protons, along with some heavier nuclei, all streaming outward with enough energy to travel far beyond the planets. As this wind moves outward, it creates an enormous bubble, called the heliosphere, that encompasses all the planets and extends billions of miles into space. Think of it like a boat moving through water, creating a bow wave and a wake. The sun moving through the galaxy creates a similar disturbance in the interstellar medium, The heliopause itself is the outer edge of this bubble, the boundary layer where the pressure from the solar wind pushing outward finally equals the pressure from the interstellar medium pushing inward. At this point, the solar wind slows down dramatically, becomes compressed, and eventually gets deflected to flow along the boundary rather than continuing outward. Crossing the heliopause means entering a region where interstellar particles outnumber solar particles, where the magnetic field is no longer dominated by the sun's magnetic field, and where the radiation environment changes fundamentally. This boundary is dynamic, expanding and contracting based on the sun's 11-year activity cycle and the varying conditions of the surrounding interstellar space. On average, the heliopause sits at roughly 11 to 14 billion miles from the sun, though this distance varies considerably. When spacecrafts cross this boundary, they're entering what we call the local interstellar medium, the space between stars that forms the substance of our galaxy. In this sense, crossing the heliopause represents a genuine transition from the solar system into interstellar space, making it a meaningful boundary for our purposes. However, there's another boundary, far more distant and far more diffuse, that represents the ultimate extent of the sun's gravitational influence. This is the Oort Cloud, a vast spherical shell of icy objects that surrounds the solar system at distances that dwarf the heliopause. Named after Dutch astronomer Jan Oort, who theorized its existence in 1950, this cloud represents the source of long-period comets that occasionally visit the inner solar system on orbits taking thousands or millions of years to complete. The Oort Cloud is thought to begin somewhere around 2,000 times the Earth's sun distance, which astronomers call 2,000 astronomical units, or AU, placing its inner edge at roughly 186 billion miles from the sun. Even more remarkably, the cloud is believed to extend outward to somewhere between 50,000 and 200,000 AU, with some estimates suggesting it could reach as far as 3.2 light-years from the sun. At these distances, we're talking about roughly half the distance to the nearest star system, Proxima Centauri. The objects in the Oort cloud, numbering perhaps in the trillions, are gravitationally bound to the sun. They orbit our star, albeit in extremely long elliptical paths that carry them to these tremendous distances. This gravitational binding represents a fundamental connection to the solar system. These objects were likely formed in the region of the giant planets during the solar system's youth, and were subsequently ejected to these distant orbits by gravitational interactions with Jupiter, Saturn, Uranus, and Neptune. They remain in solar orbit rather than drifting off into interstellar space, held by the sun's gravity even at these enormous distances. This makes the Oort cloud a legitimate component of the solar system, and by some definitions, you haven't truly left the sun's domain until you've passed beyond it. The outer edge of the Oort cloud represents the point where the sun's gravitational influence becomes weaker than the gravitational tug of other stars and the overall gravitational field of the Milky Way galaxy. Beyond this point, objects are no longer bound primarily to our sun, but rather to the galaxy as a whole. The distinction between these two boundaries, the heliopause and the outer edge of the Oort cloud, creates two very different answers to our question about how long it takes to leave the solar system. By the heliopause definition, we're talking about a distance of roughly 11 to 14 billion miles. By the Oort cloud definition, we're discussing distances of 1 to 3 light-years, or about 6 to 18 trillion miles. These aren't just different answers, but answers that differ by a factor of 500 to over 1,000. This dramatic difference underscores why defining terms matters so much in science, and why the question of how long it takes to leave the solar system doesn't have a single simple answer. The journey time depends entirely on which boundary you're trying to cross. To answer our question with actual data, rather than just theory, we turn to humanity's first and so far only artificial emissaries that have actually left the solar system by the heliopause definition. The Voyager missions stand as perhaps humanity's most successful deep space exploration program, having transformed our understanding of the outer planets while continuing to return valuable data about the outer solar system and the transition to interstellar space decades after their launch. The story of the Voyager program begins with the fortunate alignment of the outer planets in the late 1970s, a geometric configuration that occurs only once every 175 years. This alignment made possible a trajectory called the Grand Tour, where a single spacecraft could visit multiple outer planets using gravity assists, where each planet's gravity would accelerate the spacecraft and bend its path toward the next destination. NASA launched Voyager 1 first, on August 20th, 1977, followed by Voyager 2 on September 5th of the same year. Despite launching second, Voyager 1 traveled on a faster, shorter trajectory that would allow it to reach Jupiter and Saturn before its twin. Both spacecraft were equipped with identical scientific instruments and were built to survive the harsh environment of deep space for at least 5 years, long enough to complete their primary missions of exploring Jupiter and Saturn. The fact that both spacecraft remain operational and in contact with Earth nearly 50 years later stands as a testament to the engineering excellence of their design and the dedication of the teams that continue to operate them. Each Voyager weighs about 1,700 pounds and carries a suite of instruments including cameras, spectrometers, magnetometers, and particle detectors, all designed to study the planets, their moons, magnetic fields, and surrounding environments. Perhaps most famously, each Voyager also carries a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth, intended as a message to any intelligent extraterrestrial life that might encounter the spacecraft in the distant future. Voyager 1's journey to the edge of the solar system provides us with a concrete timeline for understanding what leaving the solar system actually entails in practice. The spacecraft launched from Cape Canaveral on September 5, 1977, beginning a journey that would eventually make it the most distant human-made object from Earth. Its first major milestone came in March of 1979, when it began its encounter with Jupiter, making its closest approach to the giant planet on March 5th at a distance of about 217,000 miles from the cloud tops. The gravitational assist from Jupiter increased Voyager 1's velocity and bent its trajectory towards Saturn, which it encountered in November of 1980. The spacecraft made its closest approach to Saturn on November 12th, passing within 77,000 miles of the cloud tops and within 4,000 miles of Saturn's largest moon, Titan. This encounter with Saturn provided another gravitational boost, but also bent Voyager 1's trajectory upward relative to the plane of the solar system, sending it on a path that would carry it out of the planetary neighborhood forever. After Saturn, Voyager 1 had no more planets to visit. Its primary mission complete, the spacecraft continued outward, becoming what mission scientists call an interstellar mission. In 1990, when Voyager 1 was about 3.7 billion miles from the Sun, ground controllers commanded it to turn its camera back toward the inner solar system and take a series of images that would become known as the family portrait of the solar system. One of these images captured Earth as a pale blue dot, barely visible against the vastness of space, inspiring Carl Sagan's famous reflection on humanity's place in the cosmos. After taking these images, the Voyager 1's cameras were turned off permanently to conserve power, and because there would be nothing more to photograph in the darkness ahead. The spacecraft continued its outward journey, crossing the orbit of Pluto in 1991, though Pluto itself was elsewhere in its orbit at the time, and the spacecraft was traveling through a different region of space. As Voyager 1 continued outward through the 2000s, it began encountering increasing evidence that it was approaching the boundary of the heliosphere. In 2004, the spacecraft crossed what's called the termination shock, a boundary located at roughly 94 astronomical units, or about 8.7 billion miles from the Sun, where the solar wind suddenly slows from supersonic to subsonic speeds as it begins to feel the pressure of the interstellar medium ahead. After crossing the termination shock, Voyager 1 entered a region called the heliosheath, a turbulent boundary layer where the slowed solar wind is compressed and heated. The spacecraft spent the next 8 years traversing this region, with scientists watching its instruments carefully for signs that it had reached the heliopause itself. This detection proved challenging because the heliopause doesn't announce itself with a single dramatic change. Instead, multiple measurements had to be analyzed to determine when the crossing occurred. In August of 2012, Voyager 1's instruments detected a sudden increase in the intensity of galactic cosmic rays, high-energy particles that originate outside the solar system, while simultaneously detecting a decrease in the intensity of lower-energy particles that originate from the Sun. Over the following weeks, these changes intensified, suggesting the spacecraft had crossed a significant boundary. However, scientists remained cautious about declaring that Voyager 1 had entered interstellar space because one key measurement, the direction of the magnetic field, hadn't changed as expected. According to models, crossing the heliopause should cause the magnetic field direction to shift significantly, but Voyager's magnetometer continued to show a field aligned with the Sun's magnetic field. This puzzle took months to resolve, as scientists realized that the heliopause was a more complex boundary than anticipated, and that magnetic field lines connected to the Sun might extend beyond the heliopause. Eventually, after careful analysis of all the data, NASA announced in September of 2013 that Voyager 1 had indeed crossed the heliopause in August of 2012, at a distance of approximately 11.6 billion miles or 121 astronomical units from the Sun.
This crossing occurred 35 years after launch. To put that in perspective, a person born on the day Voyager 1 launched would have been a middle-aged adult when the spacecraft exited the heliosphere. The spacecraft had been traveling at approximately 38,000 miles per hour, or 17 kilometers per second relative to the Sun, a velocity that seems astounding by terrestrial standards, but translates to only about 3.6 astronomical units per year at cosmic scales. At this speed, Voyager 1 had taken more than 3 decades to traverse the heliosphere, the protective bubble our Sun creates in interstellar space. Since crossing the heliopause, Voyager 1 has continued outward into the local interstellar medium, sending back data about this previously unexplored region. As of 2025, the spacecraft is over 15 billion miles from Earth and continues to transmit data, though its power supply steadily weakens. Scientists expect Voyager 1 to have enough power to operate at least some of its instruments until approximately 2025 to 2030, after which it will become a silent ambassador, continuing its journey through the galaxy, but no longer able to tell us what it finds. Voyager 2 followed a different trajectory than its twin, and its journey to interstellar space unfolded on a different timeline, with unique scientific value. Launched 16 days before Voyager 1, but on a slower trajectory, Voyager 2 visited all 4 of the outer planets, completing the grand tour that the fortunate planetary alignment made possible. After encountering Jupiter in July of 1979 and Saturn in August of 1981, Voyager 2 continued to Uranus, making its closest approach in January of 1986, and finally to Neptune in August of 1989. These encounters with Uranus and Neptune marked humanity's first and so far only close-up observations of these distant ice giants. The gravitational assist from Neptune bent Voyager 2's trajectory southward relative to the plane of the solar system, in contrast to Voyager 1's northern trajectory, meaning the twin spacecraft are exploring opposite sides of the heliosphere as they leave the solar system. Voyager 2 crossed the termination shock in August of 2007, several years after Voyager 1, and at a different location around the heliosphere, at approximately 84 astronomical units from the Sun, compared to Voyager 1's 94 AU crossing. This difference in crossing distance revealed important information about the asymmetric shape of the heliosphere, showing that the southern hemisphere is somewhat compressed compared to the northern hemisphere. After crossing the termination shock, Voyager 2 spent 11 years traversing the heliosheath, a longer duration than Voyager 1's 8-year crossing, again due to the heliosphere's asymmetric shape. On November 5, 2018, 41 years after its launch, Voyager 2 crossed the heliopause at approximately 119 astronomical units from the Sun, entering interstellar space just 2 AU closer to the Sun than where Voyager 1 had crossed 6 years earlier. What made Voyager 2's heliopause crossing particularly valuable to science was that unlike Voyager 1, its plasma science instrument was still functioning. This instrument measures the density, temperature, and speed of charged particles in the surrounding environment, providing direct measurements of the solar wind and interstellar plasma. When Voyager 1 crossed the heliopause, its plasma instrument had been broken since 1980, forcing scientists to infer the crossing through indirect measurements. Voyager 2's working plasma instrument detected a sharp drop in the temperature and density of solar wind particles, and a sharp increase in the density of interstellar plasma at the heliopause boundary, providing the first direct measurements of this transition. The data revealed that the heliopause is a surprisingly sharp boundary, with the transition from solar-dominated to interstellar-dominated plasma occurring over a distance of less than 1 astronomical unit. This sharp transition was unexpected by many scientists, who thought the boundary might be more gradual and fuzzy. Voyager 2's measurements also showed that the magnetic field in the local interstellar medium is stronger than Voyager 1 had measured, suggesting variability in the interstellar environment around different parts of the heliosphere. The fact that both Voyagers crossed into interstellar space after 35 and 41 years respectively gives us a concrete answer to how long it takes to leave the solar system by the heliopause definition, at least at the speeds these spacecraft traveled. However, to truly appreciate these timescales, we need to put the Voyager's velocity into perspective by comparing it to other fast objects humans have created and natural phenomena we understand. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. This is roughly 55 times faster than a typical commercial airliner cruising at 700 miles per hour. If you could drive a car at Voyager 1's speed, you could travel from New York to Los Angeles in about 4.5 minutes. You could circle Earth's equator in about 39 minutes. These comparisons make Voyager 1 sound phenomenally fast by earthly standards. Yet when we scale up to cosmic distances, the picture changes dramatically. At Voyager 1's speed, it would take about 73,000 years to travel 1 light year. The distance light travels in 1 year at its speed of 186,000 miles per second. This means that Voyager 1 is traveling at about 0.0014% the speed of light. At this velocity, despite being the fastest object to leave the solar system so far, Voyager 1 is barely creeping through space on cosmic scales. The spacecraft is heading roughly in the direction of the constellation Ophiuchus and will pass within 1.6 light years of a star called AC plus 79 3888 in about 40,000 years, though by then it will have long since fallen silent. To reach Proxima Centauri, the nearest star to our Sun, at 4.24 light years away, Voyager 1 would need about 73,000 years, though it isn't actually heading in that direction. These numbers underscore a humbling reality about space travel. Even moving at velocities that seem impossibly fast by terrestrial standards, reaching even the nearest neighboring star systems requires timescales longer than human civilization has existed. While the Voyagers hold the distinction of being the first spacecraft to leave the solar system, they aren't the only human-made objects heading for interstellar space. New Horizons, which launched from Cape Canaveral on January 19, 2006, holds the record for the fastest spacecraft ever launched from Earth. The spacecraft left Earth at approximately 36,000 miles per hour, though its velocity relative to the Sun has varied throughout its mission due to gravitational interactions with celestial bodies. New Horizons was built with a specific mission in mind: to explore Pluto and its moons, something no spacecraft had done before. After a journey lasting 9.5 years and covering 3 billion miles, New Horizons flew past Pluto on July 14, 2015, returning stunning images and data that revolutionized our understanding of this distant world. The mission revealed Pluto to be a geologically active world with towering ice mountains, vast frozen plains, and a complex atmosphere, far more interesting than the boring ice ball many had expected. After its Pluto encounter, New Horizons continued into the Kuiper Belt, a region beyond Neptune populated by thousands of icy bodies left over from the solar system's formation. On January 1, 2019, the spacecraft flew past a small Kuiper Belt object officially named Arrokoth, but nicknamed Ultima Thule during the mission, becoming the most distant object ever visited by a spacecraft at 4 billion miles from Earth. Following this encounter, New Horizons continued its outward journey,
studying the Kuiper Belt environment and searching for additional flyby targets, though its primary mission objectives had been accomplished. As of 2025, New Horizons is traveling at approximately 31,000 miles per hour relative to the Sun, and is about 58 astronomical units from the Sun, making it currently the fifth most distant spacecraft from Earth after Voyagers 1 and 2 and Pioneers 10 and 11. Given its trajectory and speed, when might New Horizons reach the heliopause and enter interstellar space? The heliopause distance varies based on direction and solar activity, but using the approximate distance where the Voyagers crossed as a guide, around 120 astronomical units, we can estimate New Horizons' timeline. At its current speed of roughly 3 astronomical units per year, New Horizons would reach 120 AU in approximately 20 more years from its 2025 position, suggesting a heliopause crossing around 2045, or roughly 39 years after launch. This timeline is similar to the Voyager's journey times, which makes sense given that all 3 spacecraft are traveling at comparable, though not identical velocities. However, there's significant uncertainty in this estimate because the heliopause position changes over time with the solar cycle, and because New Horizons might cross the heliopause at a different distance than the Voyagers, depending on its direction relative to the heliosphere's asymmetric shape. Unlike the Voyagers, New Horizons doesn't carry instruments specifically designed to detect the heliopause crossing, which means the precise moment of its transition into interstellar space may be harder to determine. Looking at the Voyagers and New Horizons together reveals a fundamental mathematical relationship between speed and time for leaving the solar system that shapes all discussions of interstellar travel. The relationship is simple in principle. Travel time equals distance divided by speed. To reach the heliopause at approximately 11 billion miles, a spacecraft traveling at 35,000 miles per hour would need about 36 years. Double the speed to 70,000 miles per hour, and you halve the time to about 18 years. This inverse relationship means that increasing speed has dramatic effects on journey time, but it also reveals a challenging reality about space travel. Current chemical rocket technology, which powered all existing interstellar spacecraft, has fundamental physical limits on the velocities it can achieve. These limits arise from the basic physics of rocket propulsion, where a spacecraft's final velocity depends on the exhaust velocity of its propellant and the ratio of its initial mass, including propellant, to its final mass after the propellant is expended. For chemical rockets, exhaust velocities max out at roughly 2.5 to 4.5 kilometers per second, depending on the propellant combination. To achieve high final velocities requires carrying massive amounts of propellant, but that propellant itself has mass that must be accelerated, leading to the tyranny of the rocket equation, where the required propellant mass increases exponentially with desired final velocity. The spacecraft that have left the solar system achieve their velocities primarily through gravitational assists from giant planets, rather than raw rocket power, effectively borrowing orbital energy from the planets to boost their speed. Even with these assists, they barely achieve velocities of 0.02% the speed of light. Reaching significantly higher velocities, and thus dramatically reducing journey times to the solar system's edge and beyond, requires fundamentally different propulsion technologies than chemical rockets can provide. This realization has led scientists and engineers to explore numerous theoretical propulsion systems that, in principle, could push spacecraft to much higher velocities than current technology allows. One of the most conceptually powerful approaches is nuclear pulse propulsion, perhaps best exemplified by Project Orion, a study conducted in the late 1950s and early 1960s at General Atomic. The Orion concept was audacious, almost absurdly so. The spacecraft would carry thousands of small nuclear bombs, each roughly equivalent to tactical nuclear weapons in the kiloton range. The spacecraft would eject these bombs one at a time behind it, determine them, and ride the blast wave forward. A massive steel pusher plate at the rear of the spacecraft, attached to the crew compartment through shock absorbers, would absorb the energy from each nuclear explosion, converting it into forward momentum. Ejecting and detonating these bombs at a rate of roughly 1 per second, the spacecraft would accelerate with each explosion, eventually reaching velocities that chemical rockets could never achieve. The calculations performed during Project Orion suggested that such a spacecraft could reach speeds of approximately 3 to 5% the speed of light, given enough nuclear fuel. At these velocities, reaching the heliopause would take only days to weeks rather than decades. A spacecraft traveling at 3% light speed would cross 11 billion miles in about 5 days. Suddenly, the edge of the solar system seems within reach, transforming from a destination requiring human lifetimes to one requiring less than a week. Project Orion studies even explored more ambitious variants using thermonuclear fusion bombs that might reach 10% light speed, reducing the journey to the heliopause to mere days and making trips to nearby stars conceivable within human lifetimes. At 10% light speed, Proxima Centauri would be only 42 years away, and the outer edge of the Oort Cloud could be reached in decades rather than millennia. However, Project Orion never progressed beyond theoretical studies and small-scale experiments for several compelling reasons. The most obvious challenge is environmental. Building a spacecraft propelled by thousands of nuclear explosions raises profound concerns about nuclear proliferation, as the technology could potentially be weaponized. More immediately, the 1963 Partial Nuclear Test Treaty prohibited nuclear explosions in space, effectively making the Orion concept illegal under international law. Beyond these obstacles lie significant engineering challenges. The pusher plate would need to withstand thousands of nuclear explosions, each subjecting it to extreme heat and radiation. The shock absorbers would need to smooth out the violent pulses of acceleration to levels humans could survive. The spacecraft would need to carry an enormous mass of nuclear explosives, presenting safety challenges during launch and assembly. Despite these obstacles, Project Orion demonstrated that technologies capable of dramatically reducing interstellar journey times are not physically impossible, but rather require solving enormous engineering and environmental challenges. Other theoretical propulsion concepts explore different approaches to achieving high velocities. Nuclear fusion rockets would use the energy from controlled fusion reactions to heat and expel propellant at very high speeds, potentially achieving exhaust velocities of thousands of kilometers per second, compared to the few kilometers per second of chemical rockets. Such engines could accelerate spacecraft to a substantial fraction of light speed, given enough time and fuel. Antimatter rockets represent the ultimate in energy density, as matter-antimatter annihilation converts mass into energy with 100% efficiency, according to Einstein's famous equation, E equals mc squared. Even tiny amounts of antimatter could provide enormous energy if we could produce, store, and control it safely, which remains far beyond current capabilities. Bussard ramjets would theoretically scoop up hydrogen from interstellar space and use it as fusion fuel, avoiding the need to carry massive fuel tanks, and potentially enabling continuous acceleration throughout a journey. Each of these concepts offers tantalizing possibilities for fast interstellar travel, but remain theoretical, awaiting breakthrough developments in physics, engineering, and material science before becoming practical. While these exotic propulsion systems remain firmly in the realm of future technology, two more modest approaches offer realistic paths for missions in the coming decades that could reduce journey times to the solar system's edge compared to current chemical rocket technology. Ion drives, also called ion engines or ion thrusters, represent one of these proven technologies. Unlike chemical rockets that burn fuel to create thrust through hot exhaust gases, ion drives use electricity to accelerate ions, electrically charged atoms, to very high speeds and expel them to create thrust. The key advantage of ion drives is their extremely high exhaust velocity, typically 30 to 90 kilometers per second, roughly 10 to 30 times higher than chemical rockets. This high exhaust velocity
means that ion drives can achieve much higher final spacecraft velocities for a given amount of propellant compared to chemical rockets, making them far more efficient for missions to the outer solar system and beyond. The catch with ion drives is that they produce very low thrust. While a chemical rocket might produce thousands or millions of pounds of thrust, an ion drive might produce only a fraction of a pound. This means ion drives cannot launch spacecraft from Earth's surface. They simply lack the thrust to overcome gravity. However, once in space, ion drives can run continuously for months or years, slowly but steadily accelerating the spacecraft to high velocities. Several successful missions have already demonstrated ion propulsion technology. NASA's Deep Space One, launched in 1998, was the first spacecraft to use ion propulsion as its primary propulsion system. More recently, NASA's Dawn mission, launched in 2007, used ion drives to visit two large asteroids in the main asteroid belt, Vesta and Ceres, becoming the first spacecraft to orbit two extraterrestrial bodies in a single mission, a feat impossible with conventional propulsion. For future missions to the outer solar system and beyond, ion drives could accelerate spacecraft over periods of years to velocities perhaps 2 to 3 times those achieved by the Voyagers and New Horizons, potentially reducing journey times to the heliopause to 15 to 20 years rather than 35 to 40 years. Solar sails represent an even more radical departure from conventional rocket propulsion, using no propellant at all. A solar sail is an enormous, ultra-thin reflective sheet, often just a few micrometers thick, that catches photons from the sun just as a sailboat's sail catches wind. Though individual photons carry tiny amounts of momentum, the vast numbers striking a large sail create measurable thrust. The key advantage of a solar sail is that it requires no propellant, meaning the spacecraft's mass doesn't decrease as it accelerates, and the sail can continue accelerating as long as it receives sunlight. Near Earth, solar sails produce even less thrust than ion drives, typically fractions of a milligram of thrust per square meter of sail area. However, like ion drives, solar sails can operate continuously, and unlike ion drives, which require electrical power that decreases with distance from the sun, solar sails work anywhere sunlight is available. Several missions have tested solar sail technology with promising results. JAXA, the Japanese space agency, launched Icaros in 2010, which became the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space during a mission to Venus. NASA's NanoSail D2, launched in 2010, demonstrated solar sail deployment in Earth orbit, while the Planetary Society's LightSail 2, launched in 2019, successfully demonstrated controlled solar sailing in Earth orbit, raising its orbit using only sunlight pressure. For missions to the edge of the solar system, solar sails face a significant challenge. The sun's light becomes weaker with distance, following an inverse square law. At Jupiter's distance, sunlight is 25 times weaker than at Earth. At the heliopause, it's about 14,000 times weaker. This means solar sails are most effective for building up speed in the inner solar system before coasting to their distant destinations. With sufficiently large sails and patient acceleration over several years in the inner solar system, future solar sail missions might reach velocities comparable or exceeding current spacecraft, potentially reaching the heliopause in 25 to 30 years rather than 35 to 40 years. Having discussed leaving the solar system by the heliopause definition, we must now confront the dramatically different timeline that emerges when we consider the Oort Cloud as the solar system's true boundary. By this definition, you haven't truly left the solar system until you've escaped the sun's gravitational dominance and moved beyond the vast sphere of icy bodies that orbit our star at distances up to 3 light-years or even farther. This definition is less about the transition from solar-dominated to interstellar-dominated environments, which occurs at the heliopause, and more about gravitational allegiance. Objects in the Oort cloud, despite their enormous distances from the sun, remain gravitationally bound to it, orbiting in the sun's gravitational well. Only beyond the Oort cloud does the sun's gravity become weak enough that the gravitational influence of other stars and the Milky Way galaxy's overall gravitational field become dominant. Calculating when the Voyagers will reach the outer edge of the Oort cloud requires estimating the cloud's extent, which remains highly uncertain.
since we've never directly detected it and rely on theoretical models based on comet observations and orbital dynamics. Most estimates place the outer boundary somewhere between 50,000 and 200,000 astronomical units from the Sun, with 100,000 AU often used as a rough middle estimate. At Voyager 1's current speed of about 3.6 AU per year, reaching 100,000 AU would require roughly 28,000 years. By the more conservative 50,000 AU estimate, Voyager 1 would need about 14,000 years, while by the more expansive 200,000 AU estimate, the journey would take over 50,000 years. These aren't typo errors or exaggerations. We're discussing timescales comparable or longer than human civilization has existed. The pyramids of Giza are only about 4,500 years old. The oldest known civilizations in Mesopotamia emerged about 6,000 years ago. Agriculture itself only began around 10 to 12,000 years ago. Voyager 1 won't reach the outer Oort cloud until a time farther in the future than the agricultural revolution is in the past. This sobering calculation reveals that by the Oort cloud definition, no artificial object has even remotely approached leaving the solar system. Voyager 1, despite having entered interstellar space by the heliopause definition in 2012, is only about 0.1% of the way to even the inner edge of the Oort cloud. It's as if the spacecraft has walked across your front yard and you're declaring it has left town. The Oort cloud represents the solar system's true extended neighborhood, and traversing it at current spacecraft velocities requires timescales that challenge human comprehension. Even the faster propulsion technologies we discussed earlier struggle with these distances. A nuclear pulse propulsion spacecraft traveling at 3% light speed would still need over a century to traverse the full extent of the Oort cloud from inner to outer edge. Only at velocities approaching 10 to 20% light speed do Oort cloud crossing times drop to decades, and such velocities remain firmly in the realm of theoretical physics and future technology. The journey to the edge of the solar system, whether defined by the heliopause or the Oort cloud, isn't simply a matter of distance and time, but involves profound challenges and changes to spacecraft and hypothetical human travelers over these durations. For robotic spacecraft like the Voyagers, the decades-long journey tests every component beyond its design lifetime. The Voyagers were designed for 5-year missions to Jupiter and Saturn, yet they've continued functioning for nearly 50 years. This longevity required careful engineering and conservative design choices, redundant systems, and durable materials. However, time takes its toll. The spacecraft's radioactive thermoelectric generators, which convert heat from decaying plutonium-238 into electricity, steadily produce less power as the radioactive material decays with a half-life of 87.7 years. When the Voyagers launched, their RTGs produced about 470 watts of electrical power. By 2025, this has declined to roughly 220 watts and continues dropping by about 4 watts per year. This declining power budget forces mission controllers to make difficult decisions about which instruments to keep operating and which to shut down to conserve energy. Heaters that keep components warm in the frigid environment of deep space, where temperatures hover just a few degrees above absolute zero, have been turned off for non-critical systems. Scientific instruments have been powered down one by one as the available power dwindles. Engineers estimate that by the late 2020s or early 2030s, even the most essential systems will lack sufficient power to operate, and the spacecraft will fall silent, though they'll continue their journeys through the galaxy indefinitely as silent monuments to human exploration. Beyond power constraints, the vast distances create communication challenges that grow more severe with every passing year. Radio signals travel at the speed of light, which sounds instantaneous by terrestrial standards, but becomes limiting at cosmic distances. When Voyager 1 crossed the heliopause in 2012 at about 11.6 billion miles from Earth, radio signals took 17 hours and 20 minutes to travel from the spacecraft to Earth, and another 17 hours and 20 minutes for commands from Earth to reach the spacecraft. This 34-hour and 40-minute round-trip communication time means that spacecraft operations cannot involve real-time control. Every command must be carefully planned and uploaded,
and the spacecraft must be capable of autonomous operation since ground controllers cannot respond to problems in real time. By 2025, with Voyager 1 over 15 billion miles away, the one-way light travel time exceeds 23 hours, meaning a round-trip communication cycle takes more than 46 hours. As the spacecraft continues outward, these delays will only increase, though by the time they become truly prohibitive, the spacecraft will likely have exhausted their power supplies and fallen silent anyway. The radiation environment in deep space poses another long-term challenge. Space is filled with galactic cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events to speeds approaching the speed of light. These particles can penetrate spacecraft shielding and gradually damage electronic components, bit by bit, degrading computer memory and causing occasional anomalies. The Voyagers have proven remarkably resilient to this radiation over nearly 50 years, but hypothetical missions lasting thousands or tens of thousands of years to reach the Oort Cloud's outer edge would need to address cumulative radiation damage over these extreme timescales. The spacecraft would also encounter micrometeorites, tiny particles of dust and ice that, at the spacecraft's high velocity, could cause damage despite their small size. Over thousands of years, even rare impact events become probable, potentially degrading solar panels if used, puncturing propellant tanks, or damaging critical components. Designing systems to survive these long-duration threats while remaining functional after millennia requires materials and engineering approaches we've barely begun to consider. For human travelers, the challenges multiply enormously. No human has traveled beyond low Earth orbit since the Apollo program ended in 1972, and the longest any human has continuously remained in space is about 14 months, achieved by Russian cosmonaut Valery Polyakov aboard the Mir space station in the mid-90s. Extending human spaceflight from months to the decades required to reach the heliopause, much less the millennia needed to reach the Oort Cloud's edge, introduces biological, psychological, and social challenges that dwarf current space medicine experience. The human body evolved in Earth's gravity and radiation environment, and long-duration spaceflight exposes crews to conditions that cause measurable physiological changes. In microgravity, bones lose density at roughly 1 to 2% per month, muscles atrophy without the constant loading provided by gravity, and cardiovascular systems adapt to not having to pump blood upward against gravity, potentially causing problems if crew members ever return to a gravitational environment. Radiation exposure from galactic cosmic rays and solar particle events poses long-term cancer risks, and we lack adequate shielding technology that doesn't involve prohibitively massive barriers. Studies of astronauts aboard the International Space Station have revealed changes in vision caused by intracranial pressure changes in microgravity, alterations in immune system function, and even changes in gene expression patterns. The psychological challenges of decades isolated in a spacecraft with a small crew may prove even more daunting than the physical ones. Earth would appear first as a distant blue dot, then become invisible among the stars, while the spacecraft's interior would comprise the crew's entire world. Communication delays of hours, then days, would make real-time conversation with Earth impossible, intensifying the isolation. Historical analogs from Antarctic research stations, submarine missions, and isolation studies provide some insights, but these typically last months, not decades. Maintaining psychological health, managing interpersonal conflicts in a group that cannot escape each other, and finding meaning and purpose during a journey measured in significant fractions of a human lifetime would challenge even carefully selected and trained crews. The spacecraft would need extensive recreational facilities, meaningful work to occupy the crew, and probably advanced virtual reality systems to provide psychological variety that the physically constrained environment cannot offer. For journeys to the Oort Cloud's edge lasting thousands of years, no individual could survive the journey, necessitating either suspended animation technologies that remain pure science fiction or generation ships where multiple generations would live
and die during the voyage. Generation ships introduce profound ethical questions. Children born aboard the ship never consented to a life confined to the vessel, destined to spend their entire existence as waypoints in a journey others began and others will complete. What kind of society would develop over thousands of years isolated from Earth? What would happen to human culture, language, and knowledge over these timescales? Would the descendants even remember or care about the mission's original purpose? These questions have no clear answers, but underscore how journeys to the true edge of the solar system, by the Oort Cloud definition, transcend mere engineering challenges and enter the realm of multi-generational social experiments with no historical precedent. While chemical rockets, ion drives, and solar sails represent near to medium-term propulsion technologies, some visionary proposals suggest dramatically more radical approaches that could reduce journey times to the solar system's edge from decades to days or even hours. Among the most ambitious is Breakthrough Starshot, an initiative announced in 2016 and funded by Russian-Israeli billionaire Yuri Milner, along with support from physicist Stephen Hawking and Facebook founder Mark Zuckerberg. The Starshot concept abandons rockets entirely, instead proposing to use extremely powerful ground-based lasers to push tiny spacecraft equipped with reflective light sails to relativistic speeds, meaning substantial fractions of the speed of light. The spacecraft themselves, called starships, would be miniaturized spacecraft no larger than a postage stamp and weighing only a gram or so, carrying cameras, power sources, navigation equipment, and communication lasers, all built using advanced microelectronics. Each starship would be attached to a light sail perhaps a few meters across and just a few hundred atoms thick. The revolutionary aspect of Breakthrough Starshot is the propulsion system. Rather than carrying fuel or relying on sunlight, the light sails would be pushed by an enormous ground-based laser array, potentially consisting of thousands of individual lasers combined into a single coherent beam with total power in the tens or hundreds of gigawatts. This laser beam would track the light sail as it accelerates, pouring energy into it for minutes, pushing it to velocities of around 20% the speed of light. At this velocity, the starship would cross the distance to the heliopause in roughly 2.5 days and could reach Proxima Centauri in about 20 years. Suddenly, interstellar distances that required tens of thousands of years with conventional technology become accessible within human timescales. The journey to the outer edge of the Oort Cloud, which would take conventional spacecraft thousands or tens of thousands of years, would require only several years at 20% light speed. Of course, Breakthrough Starshot faces enormous technological challenges. Building a laser array with tens to hundreds of gigawatts of optical power requires advances in laser technology and enormous amounts of energy, roughly equivalent to the output of a large power plant running continuously. Focusing that beam precisely on a small light sail thousands or millions of kilometers away requires adaptive optic systems far more advanced than those used in current astronomical telescopes to compensate for atmospheric turbulence. The light sail itself must withstand enormous heat from the laser without melting or warping, requiring advanced materials that can reflect nearly all incident laser light while maintaining structural integrity. The Starship spacecraft must be extraordinarily miniaturized, packing cameras, computers, communication systems, and power sources into gram-scale packages, pushing the boundaries of microelectronics and nanotechnology. Communication from these tiny probes at interstellar distances would require precise aim of their onboard lasers back toward Earth and enormous receiving telescopes on Earth to detect the faint signals. Despite these challenges, none of them violate known physics, and the Breakthrough Starshot initiative has funded preliminary research into key technologies with the long-term goal of launching a proof-of-concept mission later this century. If successful, Breakthrough Starshot would revolutionize not just how quickly we could leave the solar system, but would make interstellar exploration genuinely feasible. However, it's important to note that these starships would be tiny flyby probes, zipping through their targets at 20% light speed with no ability to slow down or stop.
They'd capture images and data during brief encounters lasting at most minutes or hours, then continue into the depths of space. Nevertheless, this represents a fundamentally new paradigm for space exploration, where journey time is measured in years or decades rather than centuries or millennia, making the edge of the solar system and even nearby star systems accessible within human planning horizons. Alternative schemes using similar principles have been proposed, including laser-pushed light sails for somewhat larger spacecraft that might carry more capable instruments, or even concepts for slowing down at the destination using magnetic sails that interact with the interstellar medium, though these remain even more speculative. While discussing spacecraft leaving the solar system, it's worth reflecting on the symbolic and philosophical dimensions of these missions. When the Voyager spacecraft were being designed in the 1970s, astronomer Carl Sagan and a committee he led assembled the Voyager Golden Records, 12-inch gold-plated copper discs containing sounds and images selected to portray the diversity of life and culture on Earth. Each record contains 115 images showing Earth's landscapes, mathematical and physical formulas, human anatomy, and scenes of human life and culture. They include greetings in 55 languages, from ancient Akkadian to modern Mandarin Chinese, each saying something like, "Hello from the children of planet Earth," or "Peace and happiness to all." The records contain a selection of natural sounds including surf, wind, thunder, birds, whales, and other animals, along with human sounds including footsteps, laughter, and a human heartbeat. Perhaps most movingly, each record contains 90 minutes of music from cultures around the world and across human history, from Bach and Beethoven to Chuck Berry, from Japanese shakuhachi to Senegalese percussion, from Peruvian panpipes to Indian ragas. The Golden Records also include a greeting from then United Nations Secretary-General Kurt Waldheim and a message from then President Jimmy Carter that reads in part, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Instructions for playing the record are etched onto its cover, along with a pulsar map showing Earth's location in the galaxy and symbols indicating how to decode the images and audio. The Golden Records represent humanity's message in a bottle cast into the cosmic ocean, a time capsule of human civilization as it existed in 1977. The records are mounted on the exterior of each Voyager spacecraft, where, protected from the harsh space environment, they should remain essentially unchanged for billions of years. The profound irony of the Golden Records is that the chances of them ever being found and played by extraterrestrial intelligence are vanishingly small. Space is incomprehensibly vast and empty. The Voyagers are tiny needles in a cosmic haystack billions of light years across. Voyager 1 is heading generally toward the constellation Ophiuchus and will pass within 1.6 light-years of the star AC plus 79 3888 in about 40,000 years. However, it won't actually come very close by stellar standards, and that star appears to have no planets. Voyager 2 is heading toward the constellation Telescopium and will pass within 1.7 light-years of Ross 28 in about 40,000 years. In roughly 300,000 years, Voyager 1 will pass within a few light-years of another star called Gliese 445. These are not close encounters in any meaningful sense. The spacecraft will be tiny, silent, cold objects drifting through the space between stars, undetectable except for a civilization specifically looking for them at close range with advanced sensors. The odds that either Voyager will ever be intercepted by intelligent beings who recognize them as artificial objects, recover them, and decode their contents are essentially zero. Yet this near-certain futility doesn't diminish the Golden Record's significance. They represent something profound about human nature, our desire to reach out, to communicate, to be known, even if we'll never know whether anyone hears us. The records say something important not about what's likely to happen to the Voyagers, but about who we are as a species. We're creatures who send messages we'll never know were received, who reach toward connection across distances and timescales that dwarf individual lives. who look at the cosmos and insist on being part of it rather than passive observers. Carl Sagan wrote about the Voyager missions, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet." The act of creating and launching the golden records mattered more as a statement about human aspirations than for any practical effect they're likely to have. They remind us that leaving the solar system is as much a symbolic and philosophical milestone as a physical one. The Pioneer spacecraft, which preceded the Voyagers, carried a different kind of message. Pioneer 10 launched in March 1972 and Pioneer 11 launched in April 1973, each carried a gold anodized aluminum plaque showing the outline of a man and woman, along with symbols indicating the spacecraft's origin from Earth, including a radial diagram showing our sun's position relative to 14 pulsars and the center of the galaxy. Like the Voyagers, the Pioneers are leaving the solar system, though they've received less attention in recent decades because their power supplies failed earlier and communication was lost. Pioneer 10's last weak signal was received in 2003 when it was about 7.6 billion miles from Earth, while Pioneer 11's last signal came in 1995 at about 3.7 billion miles. Both spacecraft continue outward in silence. Pioneer 10 is heading toward the constellation Taurus and will pass near the star Aldebaran in about 2 million years. Pioneer 11 is heading toward the constellation Aquila and will pass near one of its stars in about 4 million years. These missions, humanity's first to the outer solar system and beyond, now drift silently with only their plaques as evidence of their creators. While humanity sends spacecraft into the cosmos, natural objects also leave the solar system, providing interesting points of comparison. In October 2017, astronomers detected an object moving through the inner solar system on a trajectory that definitively showed it came from interstellar space, rather than originating in our solar system. Named Oumuamua, Hawaiian for scout or messenger, this object measured approximately 400 meters long and 40 meters wide, making it highly elongated and unusual in shape. Its trajectory showed it was not bound to the sun, but rather passing through our solar system from interstellar space and would exit back into interstellar space on the other side, making it the first confirmed interstellar object detected in our solar system. Oumuamua's discovery revealed that interstellar objects likely pass through our solar system regularly, though most are too faint to detect. In August 2019, amateur astronomer Gennady Borisov discovered another interstellar visitor, a comet designated 2I Borisov, which also passed through our solar system on a trajectory originating from and returning to interstellar space. These objects demonstrate that leaving and entering solar systems is part of the natural ecosystem of the galaxy, with objects occasionally being ejected from their home systems through gravitational interactions and wandering through interstellar space until potentially being captured by or passing through another star system. This raises an interesting question. Have any objects from Earth been ejected into interstellar space through natural processes? In principle, asteroid impacts on Earth can eject material at high velocities. Most ejecta from impacts falls back to Earth or achieves velocities that put it into orbit around the Sun, but don't allow it to escape the solar system. However, particularly violent impacts might occasionally eject material at velocities exceeding solar system escape velocity. The escape velocity from Earth's surface is about 11 kilometers per second, but material also needs to escape the Sun's gravity, which at Earth's distance requires an additional velocity. In principle, a rock ejected from Earth at around 70 kilometers per second in the right direction could escape the solar system. Whether such velocities are achievable in natural impact events remains debatable, but some scientists have speculated that the most violent impacts in Earth's history might have sent small amounts of material on escape trajectories. If so, rocks from Earth might be slowly drifting through interstellar space, unintentional ambassadors carrying fossilized microbes or chemical traces of terrestrial life to the galaxy. These rocks would require millions of years to cross even modest interstellar distances, making them slower messengers than even our spacecraft.
but they would have been traveling for much longer, potentially giving them a head start measured in billions of years if ejected early in Earth's history. The consideration of natural processes bringing objects into and out of solar systems, combined with the extreme timescales required to cross interstellar distances at achievable velocities, leads to perhaps the most ambitious concept humans have imagined for leaving the solar system ourselves. Generation ships designed to carry human populations across the void between stars. While we've discussed generation ships briefly in the context of reaching the Oort Cloud's edge, the concept deserves deeper exploration because it represents the only currently conceivable method for humans to physically leave our solar system and reach other star systems given foreseeable technology. A generation ship would be an enormous spacecraft, essentially a mobile habitat capable of sustaining hundreds or thousands of people through multiple generations. The ship would need to provide everything necessary for human life: breathable air recycled continuously from carbon dioxide, water recycled from waste, food grown in onboard agricultural systems, protection from radiation through thick shielding or placement of habitable areas behind propellant tanks, artificial gravity through rotation to prevent the bone loss and muscle atrophy of microgravity, and all the infrastructure of a small town, including homes, schools, hospitals, factories, and recreational facilities. Building such a ship would require resources vastly exceeding anything humanity has launched into space so far. The International Space Station, humanity's largest space structure, has a mass of about 420 metric tons and cost approximately $150 billion to build and launch. A generation ship might need to mass millions or even billions of tons to provide adequate shielding, fuel, and living space for a multi-generational voyage. Construction would likely need to occur in space, perhaps using resources mined from asteroids or the moon rather than lifted from Earth at enormous cost. The ship's propulsion system would need to accelerate this enormous mass to velocities of at least several percent of light speed to make journeys to even nearby stars completable in reasonable numbers of generations. This might require nuclear fusion engines, matter-antimatter annihilation, or other advanced propulsion technologies that remain theoretical. Even if the ship could accelerate to 5% light speed, reaching the outer edge of the Oort Cloud at 200,000 astronomical units or roughly 3 light years would require 60 years, spanning 2 or 3 human generations. Reaching Proxima Centauri at 4.24 light years would require 85 years, spanning 3 to 4 generations. The social and ethical dimensions of generation ships pose challenges as profound as the engineering ones. Who decides to embark on such a journey and who gets to go? The initial generation makes a choice to leave Earth and accept life aboard the ship, but subsequent generations born on the ship never consented to this existence. They're born into a world not of their choosing, destined to spend their entire lives as transitional generations whose purpose is to maintain the ship and raise the next generation. Only the final generation, if the journey succeeds, will experience the arrival at a new star system and potentially a new world. What kind of governance structures would such a society need? How would resources be allocated? How would population be managed to maintain genetic diversity without exceeding the ship's carrying capacity? How would knowledge and skills be preserved across generations? How would psychological health be maintained when Earth is an abstract concept from history rather than a living memory? Historical precedent from isolated human societies on Earth provides some guidance, but imperfect analogs, as even the most isolated human communities could still see natural landscapes and had some possibility of contact with other humans. Science fiction has explored generation ships extensively, often focusing on the potential for social breakdown or mission failure. What if descendant generations no longer believe in the mission and reject the discipline required to maintain the ship? What if knowledge is lost and subsequent generations don't understand the technology that keeps them alive? What if social conflicts escalate to violence in an environment where everyone is trapped together? These fictional scenarios point to real challenges that would need to be addressed in any actual generation ship design. The ship would need robust systems with extensive redundancy, knowledge preservation systems that go beyond simple records to active education, ensuring each generation understands and can maintain the technology. social structures that remain stable across generations, and perhaps most importantly, a sense of meaning and purpose that survives generational turnover. Some designs have proposed including frozen embryos or genetic material to be gestated by the arriving generation, reducing the number of people who must live their entire lives aboard the ship while ensuring genetic diversity for founding a population at the destination. Others have proposed suspended animation or hibernation technologies that would allow the original crew to sleep through the journey, though these technologies remain firmly in the realm of science fiction with no clear path to realization.
Even with all these challenges, generation ships represent something remarkable about human nature. They demonstrate that we can imagine and potentially commit to endeavors whose completion we'll never see, whose benefits accrued to descendants we'll never meet, that span timescales exceeding individual lives. In this sense, generation ships are perhaps the ultimate expression of civilization, the commitment to projects that transcend individual interests for collective benefits realized across generations. Many human endeavors share this quality in smaller doses. Planting trees we'll never see fully grown, building cathedrals that take centuries to complete, conducting scientific research whose applications emerge only decades later, investing in education whose returns benefit future generations. A generation ship simply extends this logic to its ultimate expression, a project where every single person involved sacrifices for a goal they'll never personally achieve. Whether humanity will ever build such ships remains uncertain, but the very fact that we can conceive of them, design them in detail, and seriously debate their feasibility says something profound about our species' ability to think beyond immediate horizons. The vast timescales and distances involved in leaving the solar system carry profound philosophical implications that extend beyond engineering challenges or even social considerations. They force us to confront fundamental questions about human ambition, the scale of the universe, and our place within it. Consider that the Voyager spacecraft, after traveling for nearly 50 years at velocities that would seem magical to any human before the space age, have crossed only a tiny fraction of the distance to even the inner edge of the Oort Cloud. They've entered interstellar space by one definition, but remain deeply within the solar system by another. In the time since their launch, human civilization has undergone enormous changes. The Cold War ended, the internet revolutionized human communication, the human population increased by 3 billion people, and technology transformed nearly every aspect of daily life. Yet, Voyager 1 has traveled less than 1/4% of the distance to the nearest star. This disconnect between the human timescale of change and the cosmic timescale of space travel highlights perhaps the most humbling fact about the universe. It is staggeringly, almost incomprehensibly vast, and humans are ephemeral creatures living in a tiny corner of it. Throughout most of human history, our ancestors' horizons were limited to distances they could travel in a lifetime, hundreds or perhaps thousands of miles for even the most adventurous travelers. The rise of civilization over the past 10,000 years expanded these horizons to encompass continents and eventually the entire globe. The space age, beginning in the 1950s, expanded our practical reach to the moon and our observational reach to the edge of the observable universe. Yet despite this enormous expansion of horizons, we remain fundamentally bound to Earth for the foreseeable future, with only a tiny number of humans having even reached orbit, much less ventured beyond Earth's immediate neighborhood. The vast majority of the 8 billion humans alive today will live their entire lives within a few hundred miles of where they were born, never even seeing Earth from space, much less contemplating journeys to the solar system's edge. This creates a strange tension in the human psyche. We can imagine leaving the solar system, we can calculate exactly how long it would take and what technologies it would require. We can even build and launch spacecraft that actually accomplish it. Yet the timescales involved exceed human lifespans by factors that make the endeavor feel almost abstract. When we say it takes 35 years to reach the heliopause or 30,000 years to traverse the Oort Cloud,
These durations are so far beyond immediate experience that they become statistics rather than felt realities. 35 years is longer than many people's careers, longer than most marriages, longer than most friendships. 30,000 years is longer than all of recorded human history. It's a duration in which entire civilizations could rise and fall, in which our species could evolve noticeably, in which the very landscape of Earth could change through geological processes. Yet these are the timescales required simply to leave our immediate cosmic neighborhood using technology either currently available or foreseeable within the next century or two. Some philosophers and scientists have argued that this fundamental mismatch between human timescales and cosmic timescales suggests that interstellar travel and genuine expansion beyond the solar system may never be practical for biological humans. Perhaps the universe's scale is telling us something, that we're meant to remain in our solar system, or that if intelligence spreads between the stars, it will be artificial intelligence in robotic form, unbothered by the decades or centuries of journey time, rather than biological beings constrained by lifespans and needs for food, water, and psychologically endurable environments. Others counter that human history is filled with endeavors that seemed impossible until they weren't. Crossing oceans once seemed an insurmountable challenge, requiring months or years aboard ships with horrific mortality rates, yet today we cross them routinely in hours aboard aircraft. Perhaps technologies we can't yet imagine will eventually make interstellar travel as routine as international air travel seems today, collapsing journey times that currently require decades into durations measured in months or even days. Yet there's something almost arrogant in assuming that technology will inevitably overcome every obstacle. The speed of light represents a universal limit established by the structure of space-time itself, not merely an engineering challenge to be overcome with better propulsion. Even if we could somehow accelerate spacecraft to 99% of light speed, which would require energies that dwarf anything we can currently produce, reaching the outer Oort Cloud would still require years, and reaching even nearby stars would require years to decades. Faster than light travel remains confined to science fiction, requiring physics that may not exist or may be forever beyond our ability to exploit. Perhaps the universe's message is humility. You can explore, you can expand, but you'll do so slowly, patiently, on timescales that humble individual ambitions and require commitment spanning generations or longer. In an age accustomed to instant gratification, where we're frustrated if a web page takes more than seconds to load, perhaps the universe is teaching us that some things worth doing require patience measured in human lifetimes or longer. There's also something profound in the fact that we're doing this at all. Humanity didn't need to launch the Voyagers or design mission patches saying, "Voyager, the interstellar mission." We could have focused entirely on Earth, on solving immediate problems, on working within the boundaries of our planet. The decision to reach beyond those boundaries, to expend resources on exploration that yields no immediate practical benefits, reflects something essential about human nature. We're curious. We explore. We push boundaries even when, perhaps especially when, those boundaries are formidable. The fact that leaving the solar system takes longer than human lifetimes or civilizations doesn't stop us from attempting it. Instead, it inspires us to think bigger, to plan longer, to commit to goals whose completion we'll never see. This quality, the ability to work toward distant goals and derive meaning from progress rather than only from completion, may be one of humanity's most defining characteristics. We plant trees whose shade we'll never enjoy, fund research whose applications we'll never see, build institutions meant to outlast us, and launch spacecraft that will travel long after we're gone. In this light, the question of how long it takes to leave our solar system becomes not merely a technical calculation, but a measure of how far beyond immediate horizons humanity can extend its vision and commitment. The Voyager spacecraft carry a unique form of this extended vision in their golden records. These records weren't designed to benefit anyone alive when they were created. They won't be discovered, if ever, until long after everyone who built them, programmed them, and launched them has died. They represent pure commitment to communication across time and space with no expectation of response or reward. Perhaps this is what leaving the solar system ultimately means. Not just the physical act of crossing a boundary, but the philosophical act of committing to endeavors that transcend individual lives and immediate benefits, of accepting that we're part of a story much longer than any single human lifetime, of finding meaning in being waypoints in a journey whose destination we'll never reach. In this interpretation, the Voyagers left the solar system not when they crossed the heliopause, but when they launched, carrying humanity's message to the cosmos and our commitment to exploration regardless of the timescales involved. Drawing together all these threads, we can now provide a comprehensive answer to our central question: how long does it take to leave our solar system? The answer, as we've seen, depends critically on what we mean by leave and where we draw the boundary of our solar system. By the most commonly used scientific definition, focusing on the heliopause where the sun's solar wind meets interstellar space, leaving the solar system takes approximately 35 to 40 years using current spacecraft technology, as demonstrated by Voyagers 1 and 2. These spacecraft, launched in 1977, crossed into interstellar space in 2012 and 2018 respectively, becoming the first human-made objects to leave the heliosphere and enter the space between stars. Their velocities of roughly 35 to 38,000 miles per hour, achieved through gravitational assists from the giant planets, represent the speeds at which we can currently send spacecraft to interstellar space. Future missions using more efficient propulsion like ion drives or solar sails might reduce this journey time to 25 or 30 years, while more speculative technologies like nuclear pulse propulsion could potentially reduce it to weeks or even days, though these remain theoretical. By the alternative definition focusing on the Oort cloud as the boundary where the sun's gravitational influence ends, leaving the solar system requires vastly longer timescales. The Voyagers won't reach even the inner edge of the Oort cloud for another 10 to 15,000 years, and won't pass beyond its outer edge for 30 to 50,000 years, depending on where that edge actually lies. These timescales exceed the entire span of human civilization, and require us to think about space exploration in completely different terms. At current velocities, reaching the true gravitational boundary of the sun's influence takes longer than agriculture has existed, longer than writing has existed, longer than cities have existed. Even with advanced nuclear propulsion reaching several percent of light speed, traversing the full extent of the Oort cloud would require decades to centuries, representing multi-generational journeys that challenge everything we understand about human exploration and ambition. For human travelers, as opposed to robotic spacecraft, the challenges multiply further. No technology currently exists or appears feasible in the near term for keeping humans alive and healthy during the decades required to reach the heliopause, much less the millennia required to traverse the Oort cloud. Generation shifts represent a theoretical solution for the longest journeys, but they require technologies and social structures we've barely begun to develop, along with a civilizational commitment to projects spanning multiple human generations or longer. Suspended animation remains science fiction. More realistically, human exploration beyond the inner solar system will likely remain robotic for the foreseeable future, with humans experiencing these explorations virtually through the data and images our robotic emissaries send back. The diversity of these answers, from days for speculative laser sail technology to 50,000 years for conventional spacecraft reaching the Oort cloud's edge, teaches us something crucial about the universe's scale. Space is vast beyond everyday comprehension. The distances between even neighboring stars are so great that traversing them requires either velocities approaching the cosmic speed limit, the speed of light, or patience measured in geological timescales. Our solar system, comfortable as it feels after centuries of astronomical study, represents only the tiniest bubble in a galaxy containing hundreds of billions of stars, which itself is only one of trillions of galaxies in the observable universe. The time required to leave even our local cosmic neighborhood humbles us with the realization that the universe operates on scales that dwarf human timescales by factors of thousands or millions.
Yet this humbling comes paired with inspiration. Humanity has built and launched machines that are, right now, in interstellar space, traveling farther from Earth than any human has ever ventured, continuing to send back data about regions no one had explored until then. We've demonstrated that leaving the solar system isn't merely a theoretical possibility, but an accomplished fact, even if the journey takes decades and the spacecraft are robotic rather than crude. We've proven that humans can commit to exploration projects that span careers and lifetimes, can maintain communication with spacecraft for 50 years and counting, can plan and execute missions whose completion occurs decades after their initiation. This patient determination, this ability to work toward goals whose achievement extends beyond individual lives, represents one of humanity's most remarkable characteristics. The Voyagers, Pioneers, and New Horizons continue outward as this is written, each traveling more than 1 million miles farther from Earth each day, carrying with them not just scientific instruments, but symbols of human aspiration and curiosity. They'll outlast everyone who built them, everyone who operated them, everyone alive today. In the deep future, perhaps hundreds of millions or billions of years from now, they may be the last remaining evidence that humans existed at all, still drifting silently through the galaxy long after Earth itself may have been destroyed by the sun's eventual expansion into a red giant. In this sense, they represent humanity's most enduring achievement, not just machines that work for decades, but monuments that will persist for cosmic timescales, carrying messages about who we were and what we valued. The question of how long it takes to leave the solar system, then, has multiple answers, reflecting different boundaries, different technologies, and different perspectives on what leaving means. 35 to 40 years by the heliopause definition using current technology, potentially 25 to 30 years with near-term advanced propulsion, possibly weeks or days with far future technologies like laser-pushed light sails traveling at relativistic speeds. 15 to 50,000 years to traverse the Oort Cloud at current speeds, multiple human generations even with advanced propulsion if we define leaving as escaping the sun's gravitational dominance. Each answer is correct within its own frame of reference, teaching us that simple questions about the universe often have complex, multifaceted answers that depend on how we define our terms and what assumptions we make. Most fundamentally, the diversity of these timescales teaches us about the universe's scale and humanity's place within it. We're a young species on a small planet orbiting an ordinary star in an unremarkable region of a typical galaxy. The cosmic distances that surround us are so vast that even leaving our immediate stellar neighborhood requires durations comparable to the lifespan of our civilizations. Yet despite this, or perhaps because of it, we reach outward. We build spacecraft knowing they'll travel for decades or millennia. We attach messages knowing they'll likely never be read. We commit resources to exploration that yields no immediate practical return. We do these things because exploration and curiosity are fundamental to who we are as a species, because pushing boundaries gives meaning to our existence, and because understanding our place in the cosmos matters, even when that understanding humbles us. The Voyager missions, now nearly half a century old and still returning data from beyond the heliopause, stand as perhaps the clearest embodiment of these values. Every day, these spacecraft travel deeper into interstellar space, farther from the sun, farther from Earth, farther from everything humanity has ever known. Every day they send back radio signals that take over 23 hours to reach us, whispers from the edge of our solar system describing what they find in the darkness beyond. And every day, teams of engineers and scientists, most of whom weren't even born when the Voyagers launched, work to maintain contact with these distant emissaries, to squeeze every last bit of science from their aging instruments before the power finally runs out and the spacecraft fall silent.
There's something moving about this dedication spanning generations. The engineers who designed the Voyagers in the 1970s have largely retired or passed away. The spacecraft they built continued the mission they began, operated now by people who grew up hearing about the Voyager's discoveries at Jupiter and Saturn as historical events rather than current missions. Someday, perhaps in the 2030s, the last transmission will be received, the last bit of data downloaded, and the mission will end not because the spacecraft stopped working, but because they can no longer generate enough power to maintain communication. Yet even then, the physical craft will continue their journeys, silent monuments moving through the galaxy for eons, long after humanity itself may have vanished or evolved into something unrecognizable. This continuity across timescales represents something profound about scientific exploration and human achievement more broadly. The benefits of the Voyager missions accrue not just to the people who built and launched them, but to everyone who has learned from their discoveries, to future generations who will study the data for years to come, and in a philosophical sense, to humanity as a whole, which gains understanding of its cosmic context through such endeavors. The missions cost money and required sacrifices of other priorities, yet few would argue they weren't worthwhile. They expanded human knowledge, inspired countless people to pursue science and engineering, and demonstrated what's possible when we commit to ambitious long-term projects. In this sense, the decades required to leave the solar system aren't merely obstacles to be overcome, but durations that force us to think beyond immediate horizons and short-term gains. The contrast between leaving the solar system by the heliopause definition versus the Oort Cloud definition reveals something important about how we understand boundaries and transitions. The heliopause is a relatively sharp boundary, crossed in a matter of days or weeks as spacecraft pass from the helios sheath into the local interstellar medium. Instruments detect changes in particle populations and magnetic field characteristics that clearly mark the transition. The crossing feels like an event, something that happens at a definable moment that can be dated and announced. The Oort Cloud, by contrast, is a gradual transition zone. Objects become sparser as you move outward from the inner to the outer cloud, and eventually you're in a region where the sun's gravity is no longer dominant, but there's no sharp boundary to cross, no moment when you definitively pass from in to out. This difference reflects a deeper truth about nature. Boundaries we draw are often human constructs, imposed on reality for our convenience, while nature itself frequently operates in gradients and continuums. Similarly, the question of when a journey begins or ends isn't always straightforward. Did Voyager 1 begin leaving the solar system when it launched in 1977, when it completed its planetary encounters in 1980, when it crossed the termination shock in 2004, when it crossed the heliopause in 2012, or will it only truly leave when it passes beyond the Oort Cloud tens of thousands of years from now? Each answer has validity depending on what aspect of leaving we focus on. This ambiguity reminds us that human categories and definitions, while useful for communication and understanding, sometimes oversimplify realities that are more complex and nuanced than our language easily captures. The philosophical implications extend to how we think about achievement and progress. In a culture often focused on immediate results and short-term gains, space exploration in general and missions to leave the solar system in particular offer a counterweight. Examples of endeavors that require patience, long-term commitment, and delayed gratification. The Voyager missions didn't yield their most profound results until decades after launch. The full scientific return from their heliopause crossings required 35 and 41 years of operation. Any mission to the Oort Cloud would require thousands of years, far longer than any nation or even civilization typically persists. These timescales force us to think differently about why we do things. We can't pursue such projects for immediate benefit because there is no immediate benefit. We pursue them because they matter for reasons that transcend quarterly reports or election cycles or even individual human lifespans. This perspective has relevance far beyond space exploration. Many of humanity's most pressing challenges, from climate change to biodiversity loss to sustainable development, require similar long-term thinking and commitment to outcomes we may not live to see. The same patience and dedication that enables multi-decade space missions could inform how we approach these terrestrial challenges. The same ability to commit resources to goals whose benefits accrue gradually over time could be applied to problems where short-term thinking has proven inadequate. In this sense, learning how long it takes to leave the solar system and reckoning with those timescales might teach us something applicable to life on Earth. That some things worth doing take time, require patience, and demand that we think beyond ourselves to the world we'll leave for those who come after us. The technical challenges of leaving the solar system also highlight the relationship between ambition and capability. Throughout history, humans have dreamed of possibilities that exceeded available technology, from flying like birds to traveling to the moon to communicating instantly across global distances. In many cases, the dream preceded the capability by centuries or even millennia. Yet the persistence of the dream, combined with gradual technological progress, eventually made the impossible possible. We're currently in this transition zone for several aspects of leaving the solar system. Robotic spacecraft reaching interstellar space is no longer a dream, but an accomplished fact. Small probes accelerated to relativistic speeds by laser sails remains a dream, but one that's being actively researched with no obvious physical barriers preventing its eventual realization. Human missions beyond the inner solar system remain dreams, with substantial physical and biological barriers still to overcome, but perhaps not permanently insurmountable barriers. The trajectory of technological progress over the past century gives some reason for optimism about what might become possible over the next century or two. In 1925, a century before this writing, heavier-than-air flight was barely 2 decades old, radio was cutting-edge technology, and the idea of machines escaping Earth's gravity remained largely speculative. By 2025, we'd not only reached space, but had sent spacecraft beyond the solar system, built a continuously occupied space station, and developed technologies that would seem like magic to people from a century earlier. Extrapolating this rate of progress forward is hazardous, as we don't know what fundamental barriers might exist, but it's at least plausible that technologies currently seeming impossibly far-fetched might become reality within a few centuries if human civilization persists and continues advancing. However, it's equally important to acknowledge that progress isn't inevitable, and that some barriers might prove more fundamental than others we've overcome. The engineering challenges of building generation ships are enormous, but don't violate any known physical laws. The challenge of keeping humans alive and psychologically healthy for decades or centuries in artificial environments is daunting, but might be solvable with sufficient understanding of biology and psychology. However, the speed of light represents a universal limit imposed by the structure of space-time itself. No amount of engineering cleverness will enable faster-than-light travel unless our understanding of physics is profoundly incomplete in ways we currently don't suspect. This means that even in optimistic scenarios, leaving the solar system and reaching other stars will likely always require either very high sublight velocities, which demand enormous energies, or very long journey times which demand patience and commitment. There's no obvious way around this constraint. This fundamental limit imposed by light speed has led some scientists to argue that the galaxy, if it contains other intelligent civilizations, must be a fairly quiet place where interaction between civilizations is rare or slow. If everyone faces the same light speed constraint, then even communications between neighboring star systems require years or decades for messages to traverse the distance, making real-time conversation impossible and even exchanges taking generations to complete. Physical travel between stars requiring decades, centuries, or millennia, depending on velocity, would be even more difficult. This suggests that if humanity eventually spreads beyond Earth, our descendants living around other stars might be connected by heritage and history, but would function as largely independent civilizations due to the sheer difficulty of communication and travel. The solar system we're discussing leaving would likely remain home to humans for a very long time, even if we eventually establish outposts elsewhere, simply because nowhere else is reachable on timescales that make regular travel practical.
Yet even this rather sobering assessment contains reasons for hope and inspiration. Our solar system is not a small place. The region extending to the Oort Cloud represents an enormous volume containing vast resources and possibilities for exploration and eventual expansion, if humanity chooses to pursue that path. The asteroid belt contains more raw materials than humans have ever mined on Earth. The moons of Jupiter and Saturn offer fascinating possibilities for research and perhaps eventual habitation. The Kuiper Belt and Oort Cloud contain trillions of objects that could be explored. Even confined to our solar system for practical purposes, humanity could remain busy with exploration and expansion for thousands or millions of years. Leaving the solar system entirely might be less about necessity and more about the same impulse that drove ancient humans to cross oceans despite not needing what lay on the other side: curiosity, the desire to see what's there, the urge to push boundaries simply because they exist. In this context, the spacecraft we've already sent beyond the heliopause represent the first tentative steps of a process that might continue for millennia. The Voyagers and Pioneers are pathfinders, demonstrating that the journey is possible and beginning the process of characterizing the interstellar medium we'll need to understand better if we ever send more sophisticated missions. New Horizons continues this exploration, studying the Kuiper Belt environment before it too eventually crosses into interstellar space. Future missions might follow, deliberately optimized for studying interstellar space, rather than being primarily planetary missions that happen to continue outward afterward. Perhaps within the next century, we'll launch dedicated interstellar probes using advanced propulsion to reach farther faster, equipped with instruments specifically designed to characterize the local interstellar medium, its density, composition, magnetic field structure, and cosmic ray environment. Such missions would build on the Voyager's legacy, extending our reach and understanding progressively deeper into the space beyond our solar system. Looking even farther forward, if technologies like breakthrough starshots' laser-pushed light sails prove feasible, we might eventually have the capability to send small probes to nearby star systems within human lifetimes. Such probes would leave our solar system in days or weeks rather than decades, reaching neighboring stars in decades rather than millennia. This would transform interstellar exploration from a multi-generational endeavor into something that could be planned and executed within the career span of individual scientists and engineers. The scientists who design and launch such a mission might still be alive, albeit elderly, when the first data arrives back from another star system. This possibility, while still far from certain, represents a potential future where leaving the solar system becomes a routine activity, rather than an epochal achievement, where missions to interstellar space are common enough that multiple attempts can learn from previous ones, and where the boundary between our solar system and interstellar space becomes more of a gradual transition zone that spacecraft pass through regularly rather than a profound barrier rarely crossed. Even contemplating such possibilities requires grappling with uncertainties about humanity's future. Will our civilization persist long enough to develop these advanced technologies? Will we continue prioritizing space exploration, or will other concerns take precedence? Will environmental challenges or resource limitations on Earth constrain our ability to invest in expensive space missions? Will artificial intelligence or other technological disruptions fundamentally change what space exploration means and who or what conducts it? These questions have no certain answers, but they remind us that the future isn't predetermined. The choices we make collectively about what we value, what we invest in, and what kind of civilization we want to build will shape whether leaving the solar system remains a rare achievement or becomes commonplace, whether it's accomplished by biological humans or their artificial descendants, whether it happens quickly over coming centuries or slowly over millennia. Returning to our central question one final time, we can appreciate that asking how long it takes to leave the solar system invites us into a reflection much deeper than a simple calculation of distance divided by velocity. It's a question that forces us to define our terms, to decide what boundaries matter, to confront the vast scales of cosmic space and time, and to reckon with both the limitations of current technology and the possibilities of future advancement. It's a question whose answer reveals as much about human nature, our capacity for long-term thinking, and our drive to explore as it does about the physical universe we inhabit. The spacecraft that have already left or are leaving our solar system stand as monuments to these human qualities. They represent enormous investments of time, talent, and resources in endeavors that yield primarily knowledge and inspiration rather than immediate practical benefits. They demonstrate that humans can build machines that function reliably for decades in the harshest environment imaginable. that we can maintain communication across billions of miles, that we can commit to projects spanning careers and even generations. They carry messages that say something profound about who we are, a species that reaches beyond the comfortable and familiar, that values understanding over ignorance, that sends greetings to the cosmos even knowing they'll likely never be received. The answer to how long it takes to leave our solar system is therefore not just 35 years or 30,000 years or any single number, but rather a spectrum of durations reflecting different boundaries and different technologies, all of which teach us about the universe's scale and our place within it. It's a duration long enough to humble us with the vastness of space, yet short enough that we've already accomplished it with our robotic emissaries. It's long enough to require thinking beyond individual human lives, yet short enough to be conceivable within the span of a single civilization. It's a duration that makes interstellar travel challenging but not impossible, that makes leaving our cosmic neighborhood a profound achievement but not an impossible dream.
Yet even this rather sobering assessment contains reasons for hope and inspiration. Our solar system is not a small place. The region extending to the Oort Cloud represents an enormous volume containing vast resources and possibilities for exploration and eventual expansion if humanity chooses to pursue that path. The asteroid belt contains more raw materials than humans have ever mined on Earth. The moons of Jupiter and Saturn offer fascinating possibilities for research and perhaps eventual habitation. The Kuiper Belt and Oort Cloud contain trillions of objects that could be explored. Even confined to our solar system for practical purposes, humanity could remain busy with exploration and expansion for thousands or millions of years. Leaving the solar system entirely might be less about necessity and more about the same impulse that drove ancient humans to cross oceans despite not needing what lay on the other side: curiosity, the desire to see what's there, the urge to push boundaries simply because they exist. In this context, the spacecraft we've already sent beyond the heliopause represent the first tentative steps of a process that might continue for millennia. The Voyagers and Pioneers are pathfinders, demonstrating that the journey is possible and beginning the process of characterizing the interstellar medium we'll need to understand better if we ever send more sophisticated missions. New Horizons continues this exploration, studying the Kuiper Belt environment before it too eventually crosses into interstellar space. Future missions might follow deliberately optimized for studying interstellar space rather than being primarily planetary missions that happen to continue outward afterward. Perhaps within the next century, we'll launch dedicated interstellar probes using advanced propulsion to reach farther faster, equipped with instruments specifically designed to characterize the local interstellar medium, its density, composition, magnetic field structure, and cosmic ray environment. Such missions would build on the Voyager's legacy, extending our reach and understanding progressively deeper into the space beyond our solar system. Looking even farther forward, if technologies like breakthrough starshots, laser-pushed light sails prove feasible, we might eventually have the capability to send small probes to nearby star systems within human lifetimes. Such probes would leave our solar system in days or weeks rather than decades, reaching neighboring stars in decades rather than millennia. This would transform interstellar exploration from a multi-generational endeavor into something that could be planned and executed within the career span of individual scientists and engineers. The scientists who design and launch such a mission might still be alive, albeit elderly, when the first data arrives back from another star system. This possibility, while still far from certain, represents a potential future where leaving the solar system becomes a routine activity rather than an epochal achievement, where missions to interstellar space are common enough that multiple attempts can learn from previous ones, and where the boundary between our solar system and interstellar space becomes more of a gradual transition zone that spacecraft pass through regularly rather than a profound barrier rarely crossed. Even contemplating such possibilities requires grappling with uncertainties about humanity's future. Will our civilization persist long enough to develop these advanced technologies? Will we continue prioritizing space exploration, or will other concerns take precedence? Will environmental challenges or resource limitations on Earth constrain our ability to invest in expensive space missions? Will artificial intelligence or other technological disruptions fundamentally change what space exploration means and who or what conducts it? These questions have no certain answers, but they remind us that the future isn't predetermined.
The choices we make collectively about what we value, what we invest in, and what kind of a civilization we want to build will shape whether leaving the solar system remains a rare achievement or becomes commonplace, whether it's accomplished by biological humans or their artificial descendants, whether it happens quickly over coming centuries or slowly over millennia. Returning to our central question one final time, we can appreciate that asking how long it takes to leave the solar system invites us into a reflection much deeper than a simple calculation of distance divided by velocity. It's a question that forces us to define our terms, to decide what boundaries matter, to confront the vast scales of cosmic space and time, and to reckon with both the limitations of current technology and the possibilities of future advancement. It's a question whose answer reveals as much about human nature, our capacity for long-term thinking, and our drive to explore, as it does about the physical universe we inhabit. The spacecraft that have already left or are leaving our solar system stand as monuments to these human qualities. They represent enormous investments of time, talent, and resources in endeavors that yield primarily knowledge and inspiration rather than immediate practical benefits. They demonstrate that humans can build machines that function reliably for decades in the harshest environment imaginable, that we can maintain communication across billions of miles, and that we can commit to projects spanning careers and even generations. They carry messages that say something profound about who we are, a species that reaches beyond the comfortable and familiar, that values understanding over ignorance, that sends greetings to the cosmos even knowing they'll likely never be received. The answer to how long it takes to leave our solar system is therefore not just 35 years or 30,000 years or any single number, but rather a spectrum of durations reflecting different boundaries and different technologies, all of which teach us about the universe's scale and our place within it. It's a duration long enough to humble us with the vastness of space, yet short enough that we've already accomplished it with our robotic emissaries. Its duration long enough to require thinking beyond individual human lives, yet short enough to be conceivable within the span of a single civilization. It's a duration that makes interstellar travel challenging but not impossible, that makes leaving our cosmic neighborhood a profound achievement but not an impossible dream.
Most importantly, it's a duration that reminds us that some achievements worth pursuing require patience, commitment, and the willingness to work toward goals whose completion we may never witness. In an age of instant gratification and short attention spans, the decades or millennia required to leave the solar system teaches that the universe operates on its own timescales, indifferent to human impatience. We can work within those constraints, building faster spacecraft and more efficient propulsion systems, but we cannot fundamentally escape the reality that space is vast and crossing it takes time. Learning to accept this, to find meaning in the journey rather than just the destination, to value progress and exploration even when final outcomes lie beyond our personal horizons, may be one of the most important lessons that contemplating these timescales can teach us. This patient determination to explore despite the vast distances and long durations required may ultimately be the most human thing about us, the quality that defines our species as we venture into the cosmos, one patient step at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video. Most importantly, it's a duration that reminds us that some achievements worth pursuing require patience, commitment, and the willingness to work toward goals whose completion we may never witness. In an age of instant gratification and short attention spans, the decades or millennia required to leave the solar system teach us that the universe operates on its own timescales, indifferent to human impatience. We can work within those constraints, building faster spacecraft and more efficient propulsion systems, but we cannot fundamentally escape the reality that space is vast and crossing it takes time. Learning to accept this, to find meaning in the journey rather than just the destination, to value progress and exploration even when final outcomes lie beyond our personal horizons, may be one of the most important lessons that contemplating these timescales can teach us. The Voyagers continue outward as this video concludes, just as they continued outward as you began watching it. They'll continue tomorrow, next year, next decade, growing ever more distant from the sun and Earth until finally their power runs out and they fall silent. But even silent, they'll continue their journeys, leaving the solar system more profoundly with each passing year, eventually traversing the Oort Cloud over tens of thousands of years, passing near other stars over hundreds of thousands of years, drifting through the galaxy for billions of years. They carry humanity's first physical presence beyond the solar system, our first tangible step into the cosmos beyond our birth star. That they take decades to cross the heliopause and millennia to clear the Oort Cloud doesn't diminish their achievement, but rather magnifies it, demonstrating that humanity can think on timescales that exceed individual lives, and can commit to explorations whose value lies not in immediate returns, but in expanding the boundaries of human knowledge and presence. This patient determination to explore despite the vast distances and long durations required may ultimately be the most human thing about us, the quality that defines our species as we venture into the cosmos one patient step at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.